Hello everyone! This is a continuation of the previous tutorial in which we created a simple dithering effect that can be used to simulate, for example, low quality film or interference in a TV signal on an old screen. And as I promised, this time we'll finish this topic by programming a shader for classic dithering with a regular structure. So let's get started. So, what will be different compared to the previous tutorial? First of all, this shader definitely won't fit on a single line, but we weren't expecting that this time either. Dithering using a Bayer matrix is a bit more complex, but certainly not by much. Therefore, I'll start by creating the usual scene with an image in the background, which I borrowed from our game Whispers of Prague. So let's do the usual stuff. Right-click in the scene, create new scene, 2D scene, and call it classic dithering. Okay, now I'll drag the image into the scene. So we have the usual sprite 2D node here, and in the inspector, I'll expand offset and cancel centered. I'll expand transform and reset the position to 0, 0. Okay, and scrolling down to the material section where I create a new shader material, click it, and create a new shader, which is called classic dithering.gd shader, type shader mode canvas item, and the folder shaders as usual. Create and clicking again to open it in the shader editor. Okay, and if you watched any tutorials on this channel before, you know that I always delete the unnecessary parts from the generated code, so we're left with just the fragment function, meaning I'm deleting vertex and I'm deleting light. Okay, so let's get started. First, a bit of theory. The effect we are going to create falls into the category of ordered dithering, which means, as we can see on the relevant Wikipedia page, that the threshold values for the step function are predefined this time. If you didn't watch the previous tutorial, I'll just add that we use the step function to turn the individual RGB components on or off for each pixel. And the step function needs a threshold that controls this switching. In the previous algorithm, we generated pseudo-random values for it, which resulted in the characteristic grainy noise. This time, we'll have a matrix of fixed values, so we'll get a regular and perhaps more visually pleasant result. I mentioned a matrix called the Bayer matrix. As we can again read on Wikipedia, this matrix can be computed using a general formula. For our purposes, however, it's enough to choose a predefined one. For example, this one with dimensions 4 by 4. To avoid making a mistake while copying it, I'll just paste it directly into the code as a constant, like this. Okay. Now, I'll write a function that returns the correct value from this matrix for the input coordinates of the current pixel. Since we have a 4 by 4 matrix, hence the name Bayer 4, we'll divide the screen into a 4 by 4 pixel grid, which can be done easily using the modulo function. And finally, we'll divide the result by 16, the number of elements in this matrix, because we need normalized values in the range from 0 to 1. The function will therefore look like this. So float, let's call it Bayer 4 again, and input parameter is vec2 pixel, not UV, but pixel. I'll explain briefly. And now ivec2 p is ivec2 of, as I said, modulo of pixel and 4. The remainder after dividing by 4, and let's return the value, the cell from our Bayer 4 matrix at the coordinates p.x and p.y. And as I said, normalize, so dividing by 16. Okay, notice that I used IVEC2 instead of the usual VEC2. That's because this time I need integer values as indices for the matrix cells, and this is an easy way to convert floats to ints. Okay, and now we'll use it in the fragment function. First, we'll get the value of the Bayer4 function for the current pixel. And because the operations in this function work with actual pixel coordinates rather than normalized UV coordinates, we'll use the fragchord variable this time. So the first line will look like this. Float, let's call it threshold, equals the function Bayer4 applied on, as I said, fragchord dot xy, the coordinates of the current pixel. Now we need to apply the same formula as in the previous tutorial, namely the step function and gamma correction. We created a uniform parameter for gamma correction before, so we can do the same here. So scrolling up and adding uniform float gamma with an int range, and as we know, the initial value is 2.2 and the range from 0 to 10 with the step point 0.1. All right, scrolling back to the fragment function, and the second line will therefore look like this. Color is a step function of our threshold as the threshold value, and now again power to implement the you know what, gamma correction texture of our texture and UV coordinates, and to the power of gamma value, vector 4 gamma. Okay, is this correct? Yes, the effect is finished. And I'll show more of that, or maybe not. As we can see, at least I hope it's visible on YouTube, the image is indeed composed of a regular grid of colored dots, and these dots are only in 8 different colors. And if the result seems too dark, we can set the gamma parameter to 1, like here in the shader parameters, which cancels out the gamma correction and gives us an image in almost the original colors. It's of course an illusion. Even in this case, we are not using more than 8 colors. And of course, if we want to, we can merge both lines into one, like this, replacing threshold and deleting this line. But I think that the previous version was a bit more readable after all. Once again, thank you very much for watching. An effect like this could be useful if you want to simulate a truly retro environment, or, for example, an image in newspapers that were printed in the last century. I'd also like to add that I'll include both dithering shaders, the previous one and today's, in my Godot shader pack, so if you don't feel like copying the matrix by hand, you can get all the code on the page I link to in the video description. Until then, take care, good luck with your projects, and I'll see you in the next video.